For the rest of 2.4, we're talking about the factor theorem. The factor theorem states that if you plug c into the function and you return 0, then x minus that value c must be a factor of the function. And inversely, if x minus c is a factor of the function, then you should be able to plug c into the function and get back 0. So if you go back and think about that for a second, what does the value x, when plugged into the function returning 0, mean? Well, remember that if the function equals 0, those values of x are the roots. And if you remember when we wrote the factors and set them equal to 0 and solved, then that gave us the roots. So that's the exact same kind of concept here, right? All right, so let's take a look at an example. X equals 3 means that x minus 3 is what we are claiming is a 0, or is the root, or a 0, or x minus 3 actually is the factor. So let's do synthetic division because that's so much easier, and we do have an x minus 3. Remember that the form is x minus c, so c is just 3. Write your coefficients, so we have x cubed coefficient, the negative 3 is on x squared, minus 11 is on x, and plus 6 on, or is our constant. Bring the first term down and multiply. That's going to be 6. Add down the column. Multiply again. Add down the column. And then 3 times negative 2 is negative 6. So you'll see that my remainder is 0. And that the factor x minus 3 then is, in fact, one of the factors of this function. So what do we have? We have x minus 3, and then we have, now this would be 2x squared minus 3x minus 2. So remember, it's remainder. This is the constant. And then it's x to the first and x squared terms. Now, if you'd like to find other zeros of this function, then you would try to factor this further. So let's see if we could do that. So we're looking for two numbers that, actually, hold on. We would use a method called factor by grouping. So I'm still looking for two numbers that multiply to be -4 and add to -3. All right, those two numbers would be -4 and +1. The problem with the factor by grouping, and the reason that we have to do it, is that the coefficient on x squared is not 1 here. Now, the problem with this is that we can't just go right to our factors. Instead, and let's actually get rid of this and just work on this piece for now. So we have to replace the middle term with a combination of the two things we just found. So -3x is going to become -4x plus 1x. Then we group, so we group the first two terms together plus grouping the second two terms together. And I don't need this 1 here in front of the x, so let's get rid of that. Then I need to find out, what do these things have in common? Well, the first group has a 2x in common, and that leaves me with x minus 2. Notice that the second one is already x minus 2, so I just act as though there's a 1 there, which in fact there is. And this is nice because now both of them have an x minus 2, which means that's a factor, and so is 2x plus 1. So the complete factorization is this times this. And if you don't believe that we just found that, then take a few seconds, pause the video, multiply that all back out, and prove that you get back this. All right, so if x minus 3 is a 0, right, that was from this guy, right, this thing equals 0, then we have this. Then this one tells us that x equals 2, and this tells us that x equals -1/2. So those are all of the roots of that function. So last example, we've got that x equals -3/2 is a 0. So that means that x minus a -3/2 is our 0. So we have -3/2 on the outside. And I can tell you're already dreading this example because we have a fraction. On the inside, we have 12 plus 16. We have -5 and 3, right? So x cubed squared x and no x's. So you bring down the 12 and multiply. So -3/2 times 12, that's going to be 18, right? So you could divide by 2, then multiply by -3. And that's going to be -18. So add down the column. We have -2. A negative times negative is going to result in a positive. 3/2 times 2 is going to be 3. Add down the column, we get another -2. And I notice I forgot a negative here, so let's put that in. All right, this was a -3. All right, so then -3/2 times -2 is another 3. And that's great because -3 plus 3 is 0. And that's what we needed, right? The remainder had to be 0 for this thing to be a 0 of the function. All right, so this is our constant. This is our x term. This is our x squared term. So our factors are currently x plus 3/2, right? Because it was minus a negative. Then we have 12x squared minus 2x minus 2. Okay. I'm going to do a couple things here. I noticed that everything in here has a 2 in common, so I'm going to factor that out. So I have 2 times 6x squared minus x minus 1. I'm going to do factor by grouping again. Need to find a set of values that multiply to equal -6 and add to -1. All right, so multiply and then add. Okay. Those two numbers are -3 and +2. So I'm going to replace the middle term here by -3x and a +2x. Then I'm going to group the first two and the second two. The set of the first grouping have a 3x in common, leaving me with 2x minus 1. And it's so nice because the other one is also 2x minus 1, so I get +1 times 2x minus 1. We have 3x plus 1 is one factor, 2x minus 1 is another factor, and then we just bring this guy down. So we have 2 times x plus 3/2, 3x plus 1, and 2x minus 1. Now, if we recall that this is all equal to 0, we can actually solve for the remaining roots. The 2 doesn't matter out here. If we just divide by 2, it disappears. Then this one already told us that this was -3/2. This here, right, we solve that one, we get x equals -1/3. Solving this one, we get x equals 1/2. And if you wanted to write this, say, in a set notation, you can say -3/2, -1/3, 1/2. All right, that will conclude dividing polynomials with the remainder and the factor theorems.